Hello, my name is Vladislav Yastrebov. I'm a research scientist at Centre Materials Research Lab at Tech, PSL University at St. Aris. And I'm happy to present you our joint work with our former PhD student Basava Raju Akula, now engineer at the set software at Transvalor, and with Julien Vignollet, engineer at Safran. The topic is the MorteX method and application of the MorteX method for various interface problems such as mesh tying, frictional contact, and wear. As many people in our community, in the computational mechanics community, I have recently recorded a video for WCCM, which will happen online in January next year, in a couple of months. And I decided to record, in addition, a more complete, full video, because 20 minutes was not enough to tell everything I would like to tell you. So it's a full video of the same presentation. The outline of the presentation is the following. First, I will introduce the motivation for the method for the MorteX method, and give you some examples in which it can be useful. And later I will present briefly the main ingredients of the MorteX method, such as the X-FEM, but well, it's not the full X-FEM, it's just a part of X-FEM, and the Mortar method itself. And later I will, the presentation is split into 4 main parts. I will discuss the mesh tying. Later I will introduce the regularization, which is needed in some cases. And in the end, I will show you some examples of contact simulations and wear simulations using the MorteX. So, introduction. The main motivation for this methodology is the following. In engineering practice, we often face with very complicated problems involving complex structures, complex meshes, and sometimes it could be very handy to, without doing CAD modeling or without doing some remeshing, simply be able to insert some features in the existing mesh. For example, insert a crack, properly refined and near the tip. Insert some geometrical features in small scale, for example, a circular hole here in this situation. Here in the rows, it's just a patch which we can glue on the existing mesh. Or we can insert a microstructure in some locations in which it would be important to know how the microstructure behaves. And sometimes you are faced with complicated wear problems in which materials is removed, and we need to deal with them to deal with the newly formed surfaces, which not the original surfaces of the mesh. So it's important to be able to create new surfaces and get rid of all the ones. It's not easy to do, and so we need to deal with this newly defined geometry. And in more general case, it would be even more handy if we could have a mesh, very simple regular non-regular mesh, in which we could cut an arbitrary complicated geometries using CAD models, NURB surfaces, and to handle later the contact between this just cut from the bulk mesh surface and this another part. All this can be done in the context of this MorteX method. And briefly to summarize, so we have a fine-tuned mesh of solid 1, and we would like to be able to tie this fine-tuned mesh with another fine-tuned mesh of solid 2, but not along the boundary fitted surface, but along the surface that passes through the solid 1. Also, we'd like to be able to handle contact interaction, frictional contact interaction between the external solid and a newly created, newly defined surface, embedded surface in the bulk of the original mesh. And also, it would be great if you could make propagate this embedded surface for wear simulations in order to mimic the removal of material. Okay, And all this can be done in the MorteX context, which is our solution for the problem. But there are other candidates. It's fictitious domain method, which is very similar, the X-FEM, and also niche embedded method, which are both which is very similar to what we are doing, but the method is slightly different, and I will explain the difference later. So as I said, our solution is the MorteX method, which combines a very small part of the X-FEM, namely the selective integration, as I will explain you shortly after this, and the Mortar method, classical Mortar method, which allows us to handle properly the interface problem like tying or contact along the non-conformal mesh interfaces. So to recall briefly the main ingredients, we will use the part of the X-FEM which is responsible for the void inclusion in the bulk. Let's consider a bulk mesh omega domain, and you'd like to cut along this gamma v boundary. We'd like to cut all the material from omega v. To do so, we can either enrich the elements, or we can simply use selective integration and ignore all the energy inside this completely cut out elements, and to integrate the energy only in the effective part of this blending elements shown in yellow here. And to do so, we will triangulate the cut elements, distribute Gauss points inside, and evaluate this integral inside this effective zone. That's it what we need from the X-FEM for this for the MorteX. Another part of the MorteX is the Mortar method. The Mortar method is a classical, rather classical method to glue, to tie non-conformal, non-compatible meshes along the interface, and to do so we will use the method of Lagrange multipliers. We will gap G here is the gap, it's a difference between displacement along the interface, and lambda is the field of Lagrange multipliers. So we will simply need to add this this integral to the weak form in order to handle this problem of time and ensure continuous, very smooth stress transition through the interface. It's done actually by weak satisfaction of the constraints along the interface, not a pointwise like it's done in notice segment formulations, but in a weak form, surface to surface with surface to surface integrals. And we will need to simply store Lagrange multipliers at one side of the mesh, and the interpolation which is used, phi, the interpolation function which I used for Lagrange multipliers, can be selected in an optimal way depending on the displacement interpolation on one side and another side. Okay, this is quite classical ingredients. Let's now see how we can combine these classical ingredients in order to solve mesh time problems in the MorteX context. So here we have a mesh, and we would like to glue on the top of this mesh a patch which contains a hole, and the physics inside the patch will be governed by this new mesh, and we simply need to glue this patch, this outer surface of the patch, real surface, boundary fitted surface, with the gamma V surface which passes through the bulk of the host mesh, okay, which is embedded surface. It's not so trivial, right? And to do so, we will need to evaluate the gap function, the displacement difference in displacement along on one side and another side. The only particular thing here that U1 for the boundary fitted edge, we will use classical shape functions, right? For example, in this case, it's bilinear shape functions for quadrilateral element, and it will be linear displacement along this line. But on the embedded line, it's a bit more tricky. I will show you later. But the integral that we need to add to the virtual work remains the same. So here in this example we try to glue this structure to these two elements along this interface, and you see there are two types of elements, one triangular one and another one is quadrilateral. And if you trace the displacement along this interface, we see that in triangular part it's straight, whereas in quadrilateral it's slightly bended, and it's not very surprising. Let's take a look on this following example. Here it's an element in the physical space in the reference configuration, non-deformed configuration, and we trace a straight line from here to here. And the straight line in the reference configuration in the parent space, it will be not a straight line but a curved line. And the same for the physical space in the current deformed configuration, it can also bend. Even though if the displacement along this line is computed using classical, in this case by linear shape functions with parameterization mu and eta, mu and eta will depend in non-linear way on this parameter zeta, which parameterizes the surface. And so it's a rational function of zeta, and the same for eta, it's a rational function of zeta as well. So it's more complicated than linear, quadratic, or it's not polynomial displacement. Okay, that's it which we need to keep in mind, and let's now show how it works. Here is a simple example with this patch that we glue on the host mesh, and we will compare with this the same problem, but here the patch is glued to the prepared hole for this patch to use classical mortar method. Okay, in this way. And here are the results, just analyzed with the naked eye. You can see that visually there are no difference, and there is no stress discontinuities along the interface, so everything works very nicely. Another example, the same submodeling, you would like to add some features, some fine features in the coarse mesh structure, so with 5 holes. And with MorteX we will be able simply to add this patch to the existing mesh, whereas in Mortar you will need to cut prepare a special hole of the same dimensions. Again, here is the comparison of results. We apply pressure here, we are interested in the stress state in this region, and here I show the meshes and the stresses. You see this in MorteX method there is overlapping meshes, but if you remove meshes we see that the stress state with naked eye we see they're quite the same, and there are no discontinuities across the interface. Okay, and the last example here would be how with just to demonstrate how easily we can insert a crack. The mesh is quite complicated for 2D problem, and to insert a mesh we will need to do some remeshing and so on, but with the MorteX we can prepare independently this patch with here is a crack, small crack, quite refined near the crack region, near the crack tip, and by applying simply by superposing this this patch with the host mesh we obtain nice solution. And here is the stress field near the crack tip, and you see there are no discontinuities across the interface, so it looks very nice. However, let's try to study it in a more rigorous way through the patch test. In the first patch test we will overlap two rectangles and try, like shown here, with some overlap zone, and we will apply uniform pressure on the top, and we expect to recover the same uniform pressure in the interface. We will consider different stiffness contrast between patch and the host, so stiffer host, softer host, or the same stiffness. We'll study different mesh density on the host and the patch, and different types of mesh will be used for the host mesh. aligned chords, triangles, and random chords, just perturbated chords. Here are the results. Triangles work fine in all situations, aligned chords work fine in all situations, but random chords, they demonstrate some discontinuities. Well, the scale is -1%, +1% from the reference pressure. It's not very huge, this oscillation, but still they're quite visible. Okay, especially in this case where this Mortar side, well, the patch is finer. Okay, and the solution which we found, the simplest solution that we found, it's to triangulate, simply to triangulate this chords in the blending chords in the interface. By doing so, by dividing every chord in two triangles, we don't change the number of degrees of freedom, and we ensure a P1 to P1 displacement field in the interface. So it's easy and it works. I will show here that in all cases, triangulated chords, they pass the patch test. No effect of spurious oscillations is seen in the triangulated chords. However, this test is not very demanding. There's a more demanding test which was considered by Sanders, Lawson, and Poos in their paper. Here we will try to transmit a linear distribution of axial stresses. Okay, it's a bend, and we transmit a torque through the interface, and we'd like to recover the same linear distribution of stresses in the interface. The same setup, the same parameters: material contrast, mesh density contrast, and different types of mesh for the host. And in this case, only aligned chords pass the patch test. Triangles fail, random chords fail, and random chords triangulated fail. Not all the time, but for this particular case where the patch is much stiffer and finer than the host mesh. Okay, it's the worst situation for this test. So here the triangulation does not help, and apparently all this happens because it's over-constrained the problem, and there are too many Lagrange multipliers in the interface which are stored in the patch. When the patch is fine, there are too many Lagrange multipliers and too few displacement degrees of freedom, and so we get an over-constrained problem. And our solution was, and it works. The solution is to coarse-grained Lagrange multipliers. The idea is inspired by this publication by Nicola Moes and collaborators, and Barbara Walnut as well. So the idea is to assign Lagrange multipliers only to few master nodes in the patch, and in between we will use linear interpolation, and these Lagrange multipliers are called slave because we use multi-point constraints to enforce them to lie on the line between lambda 1 and lambda 5. And the parameter of coarse graining is kappa. Here kappa equal to 4. We have 4 elements in the interface and 5 elements here, kappa equal to 5. This parameter can be selected one for the entire interface, or it can be locally adjusted automatically. And with this coarse graining technique, coarse graining interpolation, we can get rid of these spurious oscillations and the bending patch test. So when the patch is 4 times finer, starting from kappa equal to 4, and for higher kappa, we recover nice oscillation-free stress distribution. Okay, and the same for even finer patch, 12 times finer, starting from kappa equal to 12, we recover nicely smooth stress field without any spurious oscillations, which are still present for kappa equals 6 in this case. So it means that kappa, well, it's easy to understand. The kappa should be selected locally in a sense that number of degrees, dual degrees of freedom is kind of equal to the number of primal degrees of freedom in the host. That's the idea. Let's show it more in a more quantitative way. Here we consider the Eshelby problem, which has an analytical solution. We will consider a stiffer inclusion in a soft matrix, and the inclusion will be finally meshed, more finally than the host mesh. Okay, they are superposed. We put this inclusion on the top of the matrix, and we see that for kappa equal 1 to 1 there are spurious oscillations in the interface. Kappa equal to 4 there are still there, but for high kappa, and here for kappa equals 16 for example, we have a very smooth stress field with no spurious oscillations in the interface. Now let's compare them in a quantitative way. Here is the error in the stresses for the stress in the interface, and you see that for kappa equal to 1 we have very high error for given mesh, but for increasing kappa you can find an optimal value of kappa, which ensures for the given mesh the best solution with the minimal error. But for high kappa the quality of solution deteriorates because it's too coarse-grained. The stress in the interface become too coarse-grained. In terms of the mesh convergence, here this element size normalized by the radius, and here is the error in stresses. We have optimal convergence with a small error, whereas for the standard interpolation we have very high error because of the spurious oscillations in the interface. I'm not sure that we have optimal convergence here in this region, but here it's more or less optimal for higher H. That's it for the mesh time. Just to give you intermediate conclusion on this part. So the MorteX works well in most situations, but in case of high contrast in mesh density and material contrast, we get some problems, and these problems can be solved. In all cases, they can be solved by coarse-graining of Lagrange multipliers. And coarse-graining is done in a way that the number of Lagrange multipliers is equal to the number of degrees of freedom in the host mesh. In this way, the kappa can be selected automatically without any particular knowledge. Kappa only needs to know what's the mesh density on one side and another side. So it's easy to adjust automatically in the code. There is another solution for this oscillation problems. Instead of using Lagrange multipliers, and we can use the Nietzsche method. But the problem with the Nietzsche method is that it has to be stabilized, and the stabilization depends on the material contrast, on the stiffness contrast on both sides. So it's more tricky to stabilize Nietzsche method, and in addition, Nietzsche method is not very applicable to nonlinear materials. So we feel that MorteX method is an even better solution than embedded Nietzsche method in this case. Okay, now let me show you some examples for the MorteX for contact applications for contact and wear. Just to say a few words about Mortar method. It's the state-of-the-art method which allows you to recover very accurate contact fractions, normal and tangential, in the contact interface. And the price is that at every iteration, at every Newton iteration, we need to overlap two contacting meshes, do the clipping of elements, triangulation, and in order to obtain accurate evaluation of the Mortar integrals, the contact integrals. So it's a heavy, computational heavy operation, but that's the price that we pay for the accuracy that we obtain with the Mortar method. And this accuracy is needed especially for the for the wear problems in which the wear criteria often use either contact pressure or dissipate energy in the contact interface, and if you have some kinks in the interface pressure, these kinks will be imprinted in the worn surface, and if the new surface is not smooth, it will create new kinks, and so the wear profile will be very noisy. So that's why we need to have a very accurate, to capture very accurately the stress fields near the contact interface, the contact fractions. In our implementation, we use augmented Lagrangian method in its monolithic formulation. So it means that we handle at the same time, without use of algorithms, we handle at the same time primal degrees of freedom displacements and dual degrees of freedom Lagrange multipliers. That's it. And here is just to show you some animations, classical animations shown with Mortar. It's ironing of hyperelastic material, and the vertical stress component is shown. The next example is a much more tricky one. It's a Eshelby fracture test in which we have contact here, here, and here. And here we combine strongly nonlinear materials, GTN model in the interface, and viscoelastoplastic model elsewhere, and you have large deformations, contact, and strong material nonlinearities. Okay, and here it's an example of comparison of the Mortar method for the sliding over wavy surface. You can compare the stress field just with naked eye, and here is the MorteX contact in which this wavy surface was cut from the bulk mesh, and the stress field that recover almost exactly the same. I don't show the quantitative comparison, but almost exactly the same. Now let's look in a more tricky problem which has an analytical solution. It's a contact between two cylinders which we squeeze with a vertical pressure, and we apply tangential forces as well in order to start to shift them a little bit. The coefficient of friction equal to 0.2, and we'll compare the Mortar formulation, Mortar setup, and the MorteX setup in which the second cylinder is simply cut from the rectangular mesh. Okay, so here's the embedded surface which cuts the second cylinder from this bulk mesh. And the results are exactly the same for these two methods, for these two approaches, Mortar and MorteX. I will show you only MorteX because the points are superposed. And here is the contact pressure evolution for increasing vertical force. And now we start to apply tangential force, and so you see the evolution of the tangential tractions in the interface. Okay, so we can distinguish between stick region from here to here. Sorry, the stick region in the center and two slip regions on the periphery. It's not bad, but you see there are some locations at which the stress distribution traction are not very smooth. There are some oscillations in contact tractions, and it's not good for the wear problems. That's why we started to think about the solutions, and the solution that we found is to use the dual shape functions. In this, so because Legendre polynomial shape functions, classical shape functions, are supposed to be an optimal choice for this problem, but dual shape functions have different advantages, which we don't use all of them, but they're supposed to be the optimal choice as well. And what we obtain, what we see in our results, that using dual shape functions, we recover much smoother contact tractions, shown here, and for the tangential tractions, They are free of this oscillation that we saw in classical shape functions, and so they ensure much smoother solution. Okay. And here the use of this dual shape functions for this stationary wire problem suggested by Stupkevich and treated by Stupkevich and Philip Farah and collaborators in the recent paper. So it's a slider brought in contact with a rigid substrate, and later it slides and it becomes to wear out. And here there will be an embedded surface which will propagate in the bulk of the mesh. Let's see here. And so where it propagates, and it tends to the solution obtained by Farah, which is exactly the same as was compared, which was obtained by Stupkevich. It's the first example, and the second example I don't show all the results, but it's a threatened wire problem in which locally the worn volume, the thickness of the worn volume is proportional to the dissipated energy. Stiff materials, elastic materials, and coefficient of friction is 0.8. So this kind of the loading is the following: we squeeze it down with a constant force P, and we apply reciprocal displacement U. Okay, and we do many cycles. After a few cycles, we update the geometry, we propagate the embedded surface, and we solve the problem again. Propagate, solve the problem again, and so on. So it's separated, the wire update is separated from the simulation. And here I simply show how this embedded surface propagates in the bulk, the material, and the non-integrated elements, partly integrated, selective integrated elements, and full integrated elements appear here. And if you look on the stress distribution accelerated version, so here you can see that similarly to meshes penetrate, but it's not penetration, it's just a propagation of the new worn surface. And here you can see the stress fields, the vertical component, which is quite smooth, which is important to for the web applications. That's it for the presentation. I will conclude briefly. So MorteX method, it's a new method which allows to solve various interface problems, mesh time, contact problems, frictional contact problems, and wear. So wear problems require some specific algorithms, because in order to propagate this virtual surface, embedded surface, you need to handle with care, with caution, because we need to take into account local normals and so on. I didn't explain in details, maybe next time. So MorteX method works very nicely for most of problems, but sometimes it demonstrates some spurious oscillations in the interface. In order to cure them, we use coarse graining of dual variables, which is easy to adjust automatically. No need to ask user to specify the coarse grain parameter every time. And finally, we conclude that dual shape functions provide us with more accurate solutions than classical shape functions. So we are switching gradually to dual shape function, even yet we don't use all the advantages of these shape functions. So in practice, if you would like to try to handle wire problems with nonlinear materials which involve transfer of history variables, in the classical context of remeshing, what's needed to be done, we need to map history variables from a previous mesh to the newly created mesh while remeshing. It's a bit tricky, it's not always accurate, but here in the context of the MorteX method, it's much easier to do, because the transfer of history variables occurs within a single element. Within every element, we need to ensure transfer from the previous configuration of this element within one location of the embedded surface and you will create location of the embedded surface, it's much easier to do. And finally, we'd like to extend this methodology to 3D, which will be a very challenging task, but we hope to do so. That's it. Thank you for your attention. Don't hesitate to contact us if you have any questions. You can easily find our contacts on the internet, and you can check our preprints about the methodology, and we hope they will be published soon. So good luck to everybody. Goodbye. I stopped.